Good morning, everyone, and welcome to today's webinar. Before we get started, I'd like to go over a few items so you know how to participate in today's event. First, I want to give a big thank you to Lighthouse Instruments for sponsoring today's webinar. In the upper right corner of your screen, you should see a control panel. If you're joining from a mobile device, the control panel may appear on the bottom of your screen. You will have the opportunity to submit text questions to today's presenters by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will address them during the Q&A session at the end. If you have a question for a specific panelist, please notate their name with your question. Today's presentation will be available for download at the end of the webinar. You will be able to find it under the handouts pane of the control panel. I would now like to introduce Duncan from Lighthouse Instruments.
Thank you, Brooke, and thank you, PDA, for organizing and coordinating this webinar, and also thank all the participants. I know that we've had registrations from all over the world, some from time zones that are inconvenient for the time right now out of Asia, so thanks for the effort to join and participate. So the topic of today's webinar, container closure integrity of products requiring deep cold storage at -80. This is currently, I would call it a hot topic, no pun intended. And so we're looking forward. We hope that this webinar will not only be interesting, but specifically be useful for projects that you are working on. Okay. So a little bit of context and disclosure before getting into the material. So Lighthouse has a long history in the CCI application area. We introduced the laser headspace technique with help from some FDA funding more than 20 years ago. And this technique has been applied by the industry for one of the applications being CCI determination. So as an equipment supplier, we do provide equipment, but we also support customers with science-based CCI method development and validation from our own analytical laboratories. So we offer analytical services as well. And through that, we get exposed to a lot of customer issues and also help to generate a lot of data, which then allows us to hopefully pass along useful information and best practices back to the industry. And we also work with partners having expertise in other CCI and seal quality test methods, which will actually be part of this webinar, and I'll get to that in a minute. Another important point for the context of the webinar today is that regulations and best practices for CCI testing are actually currently evolving. So back in 2016, at the end of the year, USP 1207 was implemented, which was a big update on package integrity testing. The EU Annex 1 in the EU is currently being revised and also has new language around CCI testing requirements. And this has triggered in the industry and also at the regulators an evolution in how to think about CCI and testing for CCI. Speaking about those partnerships, we're very lucky today to have a co-presenter in Roger Eselta from Genesis Packaging Technologies. Roger is Vice President and Senior Advisor there, and also has been a very active PDA member over the years. I will be handing over to Roger to present some material in the middle of the presentation. So Genesis offers vial sealing platforms and associated equipment, and they also provide technical consultation and training in the primary packaging area for parenterals along those topics. So thanks for being here, Roger. So what are the webinar objectives? I've written two objectives here. I think this topic has gotten increased attention over the years, but we still need to raise awareness of what happens during deep cold storage to vial container closure integrity. So that's one of the objectives here. The second objective is that we want to present a holistic approach that you could perhaps use for minimizing the risk to CCI during deep cold storage. And to do that, we're going to use very concrete examples from projects which generated robust science-based CCI data, which enabled people to choose appropriate primary packaging components, as well as execute robust qualification of the vial sealing process. So there will actually be a lot of data presented here, and I hope it's not overwhelming, but I think our goal in doing that, that's the best way to understand what you can do, is to actually see the data. So here's the agenda. Starting off, a little bit of introduction and present data that shows the current understanding of what's happening to vial CCI during this deep cold storage. And then, as I just described, spend a lot of the webinar or the presentation looking at industry case studies, which will then demonstrate and explain this science-based holistic approach to ensuring CCI of this deep cold storage product. And we're hoping to leave enough time at the end for some Q&A. Okay, vial CCI during deep cold storage. So this has gotten increased attention in the past years, primarily because formulations are driving this, of course, formulations that potentially need this deep cold storage. And these are viral vaccines. You can think about gene therapies. And here you end up having products that potentially need storage. They need to be frozen and stored at somewhere between -60 and -85. You also have cell therapy. So that's also up and coming. Here you're talking about mostly bags, perhaps cryotubes, and here you go down to even colder temperatures, -120 to -150, or even -180. We'll be focusing on that first class that needs this deep cold storage to -80, and specifically vials. So in the past 5 to 6 years, as these formulations have been ramping up, a lot of work has been done to answer the following questions. So what happens to vial CCI during deep cold storage, number one? And number two, how does vial seal tightness correlate to maintaining CCI? And when we talk about vial seal tightness, we mean how well are these vials capped and crimped on the production line, or by hand if this is being done manually. So what do we know? What has those 5 or 6 years of more intense studies showed? So at these low temperatures, maintaining CCI of a pharmaceutical vial depends critically on a few things. So first of all, the primary packaging components. So the specific vial stopper combination and the vial stopper cap design and fit dimensions. You know, how do these components fit together and stack up? Number two, the stopper compression. So how well is this vial being capped and crimped? And thirdly, of course, specifically temperature, and specifically a temperature range around the glass transition temperature of the rubber stopper. We'll get more into that in just a minute. And what's been interesting is these studies have shown that these sealing failures that are caused by deep cold storage are actually temporary. So what happens is you can have a well-sealed or a vial that has good CCI at room temperature, put it into deep cold storage, and it loses its closure during the deep cold storage or at the deep cold storage temperatures. When you take it back out of storage, the vial warms up and it will actually reseal. And so the consequence of that is that it's a little bit more complicated to detect. You'll see down there at the bottom of your screen a reference. So this was a publication back in 2012 in the PDA journal, which goes through a lot of these things in more detail if you're interested in looking that up. Okay, so I just mentioned at very low temperatures, especially around the glass transition temperature of the rubber stopper, you start to see some physical effects happening. And number one, the rubber stopper becomes brittle. It loses its elasticity. So that's the definition of a glass transition. The material under a certain temperature becomes a glass. The second thing that happens is shrinkage. So the rubber stopper also shrinks, which can be clearly seen in X-ray tomography images such as this one. And what you see here is an image that has a blue outline. So that's the outline or form of the rubber stopper at room temperature. And then the gray image that you see is that same stopper, but now at, in this case, cryo temperatures. And so you, in this particular case, for this specific stopper, it showed that this stopper shrunk by about 8.5% by volume at cryo conditions. And what's interesting then is that a glass vial will shrink an order of magnitude less at these same conditions. So the conclusion is that this shrinkage can lead to interference gaps. So wherever you have the stopper, the vial, or the crimp interfacing with each other, they're all made of different material, a rubber stopper, a glass vial, a metal crimp, and these materials all have different coefficients of thermal expansion, which means that they will shrink at different rates. So here's a slide from a presentation given by Chris Folta at Janssen at a packaging conference a couple of years ago. And this is a similar X-ray tomography cross-section as the last slide, but now you see the full vial. And what's interesting here is you can see these interface gaps start to appear. And you have to look closely, but I've put up a red circle here to draw your attention to a point where the rubber stopper has actually started to pull away from the inside of the vial neck there. So again, physical evidence that you see these interference gaps start to appear. And of course, this can cause a potential risk to the actual closure of the vial. So what happens if you actually lose closure during deep cold storage? So we've put together some animations here, which hopefully make this a little bit more clear. So imagine you have an air-filled vial at 1 atmosphere at room temperature. So it's been filled, it's under an air headspace, it was capped and crimped, and it actually has good closure. So it's well sealed. Now imagine that this vial gets put into cold storage. And for the sake of this animation, I've picked a situation where it's put onto dry ice. So a lot of these products are often transported on dry ice. So actually what you have outside the vial is a carbon dioxide environment from the dry ice. And you may or may not have caught it in the animation, but as the vial cools down, the headspace pressure actually lowers, condenses, and creates an underpressure in the vial. So that's just the ideal gas law, which hopefully everybody remembers from high school chemistry. So then you actually create an underpressure inside this vial at the cold storage temperature. Let's say that the stopper loses its elasticity under its glass transition temperature, which for most rubbers is around in between -55 to -65 or -70. And that because of the shrinkage that also happens, interference gaps appear and the closure is lost. So what happens then? Well, now what you have is a vial that starts to ingress this cold, dense CO2 gas from the storage environment. It happens rather quickly because of this underpressure, and so you end up with a vial that fills up with CO2. So it was fine outside of deep cold storage. Inside deep cold storage, it's actually open and ingresses the cold gas from the storage environment. Now imagine that you take this vial out of storage and it begins to warm up to room temperature. At a certain temperature, the stopper actually regains its elasticity, expands, and reseals closure. So now the vial is sealed again, but this cold, dense CO2 gas is trapped inside, And as the temperature continues to rise to room temperature, the gas tries to expand and it creates an overpressure. That previous reference that I had at on one of the slides describes a situation of a viral vaccine, and one of the signs that they had that told them something might be wrong is this overpressure when a administrator took a syringe and put the syringe into the rubber stopper after the vial had thawed. They saw the plunger rod shooting up, and when they removed the syringe from the rubber stopper, you would have live viral vaccine products spraying out through the puncture hole. So not a good situation there. And again, from the ideal gas law, you can calculate that theoretically you could build up an overpressure of about 1.5 atmospheres inside the vial if you're storing at -80. So how do you detect this? Well, if you can measure the carbon dioxide in the headspace, that would verify that the vial had CCI issues in the cold storage. And if you actually measure over time, if this overpressure of CO2 is maintained, then you can also verify that these leaks that we see are temporary. And that was an important discovery in the early stages of investigating this phenomena, because what that means is the vial is sealed outside of cold storage, so traditional CCI tests will not detect these failures in CCI. So again, you imagine taking a vial at room temperature that is thawed and you do a blue dye test, it's actually sealed Okay, so how would you detect this CO2 gas that has come inside? So here's where laser-based headspace comes in, because it's exactly a technique that allows you to measure and quantify traces amount of gas inside of a sealed container. And for those of you who are not familiar with the method, it's a spectroscopic method. You shine laser light through the headspace of a container, detect how it's absorbed, and you can actually quantify what the gas conditions are inside of that closed container. And it's a non-destructive measurement, so the thing happens to the sample. It's also rapid, on the order of seconds, so it allows you to generate a lot of data in a straightforward manner. It is listed in the USP 1207 chapter. Analytical enables the development of CCI test methods based on the detection of gas ingress into a leaking container. So if you have a situation where gas is moving in and out of a container through a leak, you can measure that with headspace analysis. So just how this actually works in practice, and to give you some data here, here's an example of media-filled vials that were stored on dry ice. So again, the initial headspace conditions were 1 atmosphere of air. They are stored on dry ice for 7 days, taken out and thawed to room temperature, and then the headspace conditions were analyzed. So any change in these headspace conditions would be a direct sign that closure was lost in the storage. So of course, you could directly measure any CO2. So again, on dry ice, you could look for CO2. What we often do in development studies is also use -80 freezers that have an open box of dry ice in the freezer. Freezer itself becomes a CO2-rich environment. So then the CO2 gas you can see as a tracer gas, looking for any vials that are losing closure. So clearly here, 3 out of the 20 samples, media-filled samples, leaked during the storage on dry ice, have very high levels of CO2 inside. You can also detect this with other headspace measurements. So on the bottom left there, if you look at the headspace oxygen, it's no longer, around 20%. The same 3 vials show depleted oxygen levels, which correspond to the CO2 gas displacing the air inside the vial. And then finally on the right, this overpressure phenomena, you can also measure headspace per vial, and you see that the same 3 vials are measuring an overpressure. These are all just non-destructive measurements. 3 independent headspace measurements identified vials that had closure issues during the dry ice storage. So now you can see that you can develop techniques and test methods for detecting this gas exchange during the cold storage. So now that you have a tool for measuring or detecting and identifying defective vials or vials that are having issues in cold storage, you can then set up studies to give you information on primary packaging components, which ones fit together well, which ones work, which ones don't. Okay, now the other half of the story, this holistic approach that we're talking about, involves looking carefully at the vial sealing process. And you also want to have an analytical tool that helps you there. And so instead of just doing aesthetic visual inspection of the crimps and maybe doing the twist test with your hand to see if it's loosely capped or crimped or tightly capped, you want to have an analytical tool to help you there. And now I'll hand over to Roger, who will explain this part of the presentation. So Roger, if you could unmute and take it there.
Thank you, Derek. And thanks to Lighthouse again for sponsoring this. I'm very happy to participate and share a little bit about residual seal force testing. So before I get into that, I want to get into the idea of inherent package integrity, which is described in USP 1207. And essentially what it is, it's the leakage rate of a well-assembled, and that when we're talking about a vial system, that's the sealing process, but a well-assembled container closure system using defect-free components, meaning that the components comply with all requirements. They're not perfect, but again, they don't have significant defects. But in any case, there's always deviations that can affect that inherent package integrity. Of course, components that are out of spec or defective in some way. We don't put them together as they should be. Some damage occurs to them, or as we're talking about here, some challenging condition exists that will possibly cause failure or deviation from that inherent package integrity. Okay, I'm not advancing here.
I can advance for you, Roger.
Go ahead, thank you. There we go. So what we talk about here to help assess that inherent package integrity or to characterize a well-sealed vial is a tool that we call residual seal force testing. And it's not a CCI test as laser headspace analysis is, but it's a package seal quality test, and that relates to the consistency of the package's sealing performance. The test itself is qualitative. It helps us understand, in the case of residual seal force, how tightly that vial is sealed, and then with that information, what can we do with it to help assure that we're going to maintain integrity throughout the life cycle of that packaging system, the life cycle for that drug product. Go ahead and advance to the next one, please. So in sealing, and this is just a representation of several, or of one sealing type of several, but here you see a vial that's held in place, a pressure block or plunger comes down that pushes down on the top of the vial, and that compresses or squeezes the rubber. In this case, a sealing disc or roller comes in and crimps the metal while the rubber is compressed. And the two X-ray images you see below those show that. So you see an uncompressed rubber stopper with the aluminum seal. The aluminum is in pink here, and how that fits over the vial, and then what it looks like after the sealing process. So you can see some significant viscoelastic deformation there. the diameter, the outside diameter of the rubber has actually increased. It's now equal to or even greater than the diameter of the flange of the glass. It's been compressed in shape and in the height of the flange of the rubber. And what that does is that the applied forces create a strain in the rubber which form a contact stress. And that contact stress is what makes the seal and holds the seal and allows us to maintain that seal throughout the process. And again, when we talk about that, that's an amount of stored energy in the rubber stopper, the compressed rubber stopper, and that's our residual seal force. And we want to have a tool to measure that. Go ahead and advance there. So this is an animation of exactly what happens in the capping process. This is a horizontal view, but you can make out the rubber stopper. You can make out the vial and also the crimp. If you would want to initiate that, we'll see what happens here. Good. So obviously the stopper is inserted, but the colors, the pink being the greatest, is that surface stress, and that's where your seal, the greatest part of your seal, is occurring. And what we want to do is maintain that throughout the process. And as Derek had pointed out, when you go below the glass transition temperature, the rubber becomes somewhat rigid. It also begins to contract. And if we could continue this animation showing that, you would see that contraction, but you would also see those forces decrease, and the ability to maintain a seal would be compromised. However, what we have shown is that the tighter the seal to begin with, the more likely it will maintain sealing or integrity even in the deep cold storage temperatures. Go ahead and advance one more time. So we do that by measuring residual seal force, and that is RSF is the strain, the surface stress a compressed elastomeric rubber stopper continues to hold on the sealing surface of the vial after the crimp is in place. That number will vary over time. There is some degradation that you see. There's other factors that cause some stress relaxations. Likewise, as the temperature goes down, residual seal force goes down. When the temperature is restored, the residual seal force is also restored. So quantifying RSF is a test method that estimates the locked-in compression of the rubber stopper by measuring that energy in that locked-in compression. Enough compression is essential, of course, to seal integrity, and even more significant compression is necessary to hold CCI at those low temperatures. Go ahead, one more. So this is an illustration of how residual seal force is measured. You can see it looks somewhat like that the capping device we saw in a few slides ago. But essentially what we do is we apply a new load to the vial, and by applying that, we measure it using a load cell, and we create a stress strain curve. You see that to the left. And if we analyze that stress strain curve, go ahead to the next slide. You can see that that's the green line. Now, what you can't make out in that green line is there is a point of deflection there, which is equal to the residual seal force. Sometimes it's more distinct, and you can see it somewhat visually, I should say. But there are analytical tools that were developed a long time ago by John Ludwig and his colleagues at Pfizer, where they showed if you take the first and second derivatives of that curve and you apply certain analytical techniques, you can pinpoint exactly where that knee is and get relatively consistent residual seal force values. In this particular case, it's just over 64 newtons. And that's where that yellow horizontal line intersects the green line. To briefly summarize this, you take the first derivative of the stress strain curve and then the second derivative. The lighter blue line is the second derivative, the purple line is the first derivative. And what Ludwig shows is that the knee or residual seal force point corresponds directly with the first major peak or valley of the second derivative after the major peak of the first derivative. And his work, again, published a long time ago, peer-reviewed in the PDA journal has demonstrated this very clearly, and this technique now has been used for close to 30 years, or over 30 years, I should say. So as I mentioned, residual seal force can help us determine how well the rubber is compressed against the glass. Here we see a correlation of residual seal force to the percent of stopper compression. And in this particular work, what we did is used 4 sets of capper parameters, adjusting those parameters to increase the compression, and then we can see a corresponding increase in residual seal force. And you'll see a little later why this becomes important. Just a little observation here. If you look at the yellow dots, that's the highest force. You can see that the curve actually, or curve is actually beginning, and it's starting to go a little bit more vertical. That's as you get to the maximum compression of the rubber stopper. Go ahead one more time. So that alone isn't going to help us a whole lot. We need to do a little bit more, and at room temperature, oftentimes what we do is we want to look at the effect of residual seal force, seal tightness on some type of helium or some type of leak rate. In this example, helium is used, and this and many other studies have shown that as residual seal force increases, leak rate decreases. And at some point, you're going to go beyond your ability to measure that change, and you're going to get to essentially leak rate cutoff. And this is some work that was done by Duncan some time ago, but similar work has been repeated many, many times. Helium is a very good molecule to use. It's very sensitive, but its applications in the real world are limited. It is a destructive test. It's time-consuming. And as Derek had pointed out, it's really not going to pick up the kind of failures that we see in deep cold storage. So with that, I want to go back to Derek now, and he can take over from here. Oh, I'm sorry, I still have a couple slides left. My apologies. So where is RSF used? Certainly in package development. The effect of container closure system variables, dimensional tolerances, hardness of the rubber, the assembling process itself, and then again through distribution and storage. We do a lot of studies that use residual seal force to help us predict what's going to happen as we put the container closure systems together and how they're stored, including deep cold storage. The idea, of course, is to characterize that well-sealed vial. As you begin to set up your choose and set up your capping equipment, it can help us establish optimal capping parameters and help understand the variation that comes within the capping process. Once we know what the characteristics of a well-sealed vial are, that can help us establish the appropriate and optimal sealing parameters. And then in production, the verification of capper setup and monitoring the process. These are all useful ways to apply residual seal force. Okay, one more and I think I'm done. So a lot of work has been done, especially in the last few years, going back 10 years ago. Danik Wazo and Steve Orzos, he was with IMCLON at the time. They demonstrated that RSF values may be used effectively in setting up the vial cappers, as I'd mentioned, and monitoring the crimping process. With an understanding of compression and leak rate cutoff, which we talked about, RSF can further be used as a predictor of leakage risk. I want to emphasize here that it is a predictor of risk. It's not something that you can measure a vial's residual seal force and say this vial will leak and this vial won't. It cannot do that. It's not a leak test itself. But again, it can tell you about tightness, vial tightness, and as a group or a population can predict whether there's a likelihood or a probability that there may be some leakage within that group. A few years later, a guy who's done a lot of work in this area, Roman Mathis, originally with Roche, now with Lonza, and continuing to do work in this area, he showed that the RSF tester can be used to characterize residual seal force of a capped vial independent of the capping equipment used. And again, that's identifying or characterizing that well-sealed vial That can then allow you to compare the residual seal force and seal quality of different drug product units, regardless of where they're manufactured, on what line or what facility. A well-sealed vial is a well-sealed vial. And then last year, Robert Oveda with Genentech, he wrote in his work, the ultimate goal of capping is to achieve long-lasting CCI of the container closure system. Thus, the relationship between RSF and CCI should be understood, well understood, to allow the use of RSF during routine commercial manufacturing. So again, it can be used in these senses, and it should be, but also when we understand it well, it can be used in combination with tools like laser headspace analysis and help us design an appropriate package container closure system, as well as the capping process, and become a predictor of success even at deep cold storage temperatures. Now I go back to Derek. Thank you.
Okay, thanks, Roger. So I think with this background and context, we're in a position now to talk about this science-based holistic approach, which hopefully will help manufacturers ensuring CCI of deep cold storage product. And so I'm going to list a few things here, and then for each of these steps, show some example data to give you a better idea of how to do this. So number one, we talked about you need to have some method to actually detect a CCI failure. And once you do have a method in place, that allows you to do CCI studies, looking at different primary packaging components so that you can choose the appropriate ones, the vial stopper combination that will work for your product, but also in the deep cold storage environment. Once you've done that, then you can move and look at your process. So just as Roger explained, you want to be able to characterize the sealing performance of the production line. It's been shown in studies that a good tight seal will help in keeping CCI at these deep cold storage temperatures. And so then you want to generate some good science-based RSF CCI correlation data. We'll show a number of examples of this in a few slides. And finally, as you're developing the process, you want to then determine, this data that you're collecting here in these first steps will help you determine the acceptable limits for your capping settings on each production line. So, capping and crimping lines setups can be very different from each other, with different parameters that you use to control and set the lines, and you want to determine which will give you the best performance for sealing the vial. And then as you move, getting ready for the commercial part of the product life cycle, you want to qualify these production lines for CCI and look at your lower and upper capping limits that you've determined from the previous steps. And then finally, with a CCI method that you've developed, if you validate that method, then you can also use your CCI method for a number of things, validating the shipping process, and also perhaps even using in your program as an end of shelf life CCI test. So this slide kind of summarizes what we're calling a science-based holistic approach. Before we look at examples of the data that's generated in these various steps, I just wanted to briefly, we talk about CCI methods, and I think the industry is just getting comfortable with the idea of developing different types of CCI methods. I think there were standard methods that were used in the industry in the past. And so, as we mentioned at the beginning, this area is still evolving over the last few years. And here's a slide, I think, that explains it very simply and in one sentence. And it's from CEDAR at FDA, and it's even titled Evolution. And what it says here is, CEDAR has avoided being prescriptive to allow manufacturers to develop tests to demonstrate the container closure integrity specific for their product, process, and container closure system. So with the implementation of USB 1207 at the end of 2016, this triggered an evolution in best practices for CCI testing. And I think what the situation we're in now is that you really need an analytical toolbox of all kinds of CCI methods. And the regulator is looking for the development and demonstration of methods that are appropriate for product, process, container. And with those methods, you should be able to, number one, detect critical leaks and also generate science-based CCI data. Another slide, this time from Sieber. On the left there, you see a list of different types of container closure systems. On the right-hand side, you see a list of all kinds of different CCIT methods. The list was taken, by the looks of it, from that USP 1207 chapter. And the idea is for all these different types of containers on the left, there's no one gold standard CCI test that you can use that will be most appropriate. You have to find the one which, again, is most appropriate for your product, formulation, container configuration, and even perhaps for stage in the product life cycle. So just wanted to emphasize this point that the industry best practices for developing and using CCI tests are kind of in an evolutionary phase at the moment. Okay, so developing an appropriate method for deep cold storage product. How do you do that? So here is a data graph, and there's lots going on here. So let me try and explain it. Key to doing this is in demonstrating and making sure that you are picking up defects during the deep cold storage. And one way to do that is to do studies, method development studies with positive controls. And so here you see a number of different types of positive controls. You see some wires, different size wires here being labeled. Those are samples that have these wires in between the rubber stopper and the vial neck. So you don't know for sure if that causes a CCI defect, but it probably will. On the right-hand side, you see some LDDs. Those are laser drilled holes that are in the glass body of the vial, and you can get holes drilled that are certified to a certain dimension. So you see here 2 micron, 5 micron, 10 micron. And on the far right, you see some gross defects. So we include all of these types of positive controls in our method developments. And here, what we're plotting, again, it's a CCI test method based on carbon dioxide or detection of carbon dioxide. And so you see that all of these positive controls were detected with elevated carbon dioxide levels, meaning that they were leaking and that the test method picked them up. We were also looking at both glass and plastic vials here. You see those labeled there. And we were looking at, can you detect a leak in frozen products, so immediately after removing from deep cold storage? So that's the blue bars there. Or can you still detect these, or can you also detect these defects once the product has thawed and is at room temperature? And you see that in all those cases, you detect the defects as well. So the point of developing an appropriate method, you need to generate data that shows you're detecting a critical leak. And you also, in the end, want to generate data to validate what you can detect and when you can detect that. And so here's an example of that for a deep cold storage product. Number 2, choose the appropriate primary packaging components. So here is a data set from 10 different vial stopper combinations. These vial stopper combinations were stored on dry ice for 7 days. But here we are actually using an oxygen measurement. So if you go back to that original media fill example where we showed that different headspace measurements can be used as a CCI test method, here you're looking for samples that have depleted oxygen levels, which are an indication that CO2 has come into the vial and displaced the original air headspace. And from this data, you can see that a number of vials have depleted oxygen levels, and that certain vial stopper combinations actually have quite high failure rates. So you see set 3 there, 39 of the 50 vials show depleted oxygen levels. Set 9, 31. These are all vial stopper combinations that worked at room temperature but do not work at deep cold storage. So you need to have this robust data. You also need to have robust sample sets, so hundreds of samples. It's hard to make conclusions if you're only looking at sample sets of 5 or 10. So again, here an example of CCI data that allows you to choose appropriate primary packaging components for deep cold storage. Now we get to the other side of the coin, and that's characterizing the sealing performance of the production line. And what we're plotting here is some residual seal force data of a line before it was optimized and then after it was optimized. So the blue line there shows the RSF values that were measured on the non-optimized line. And you see that they're a little bit lower than what you would like, and they also have high variability. So going to your line and optimizing some of the capping and crimping parameters gets you to a situation which is plotted with the gray line, where the residual seal force value has gone up to an appropriate value, a little bit higher, and you also see that the variability is a lot less than before the optimization. So again, as Roger described, it's a real measurement that you can use to clearly characterize the performance of your capping and crimping and also optimize it. And again, this is a lot better than just doing the visual aesthetic inspection and doing a twist on the cap. And just as in the CCI studies, you want robust sample sets to cover all of your capping and crimping heads, and what you're really aiming for here is a statistical confidence in the process. A recent example that we had, that we participated in, hundreds of samples, actually thousands of samples were tested for every capping setting on each production line. And if you do that, you get a very clear insight into the sealing performance of your production line. Number 4, generate science-based RSF CCI correlation data. I'm going to put up a graph that has a lot going on. So again, I'll try and explain that well, but we're looking at CCI as a function of a few things: temperature, but also the capping and crimping quality as measured by RSF. So here is some example data. And again, here we're using yet another headspace measurement as the CCI indicator. So here we're looking for that overpressure phenomena that you can get. This is data from one vial stopper combination, but 4 storage temperatures. And you see a room temperature control there. You see -20, so frozen, but -20. Frozen -80, so that's below the TG of the rubber stopper, and then cryo on the very right. And we're also looking at sample sets that were capped and crimped with 3 different pressures. So a low RSF value, or a loosely capped and crimped vial, nominal RSF value, and a high RSF value. And you can see that for this vial stopper combination, you get good sealing at room temperature. You get good sealing at -20 frozen, but you start to see issues at -80. And those issues are happening with the low RSF sample set, so the loosely capped and crimped vial. So again, an indication that the process capping and crimping is important. So here you can make a risk assessment. Do I want to use this vial stopper combination, but make sure that I am robustly capping and crimping my vials? Once you get to cryo temperatures, then you see very high failure rates. And in fact, at the low or the loosely capped and crimped vials, everything fails. And you see, I believe, just a few of the vials at the high and nominal capped values holding closure, but everything else failing. So clearly you would not want to use this vial combination if you're going to go down to cryo temperatures. So again, very robust science-based data that gives you very good insight, not only into the primary packaging components, but also to how that correlates to vial sealing. Here is another set of RSF CCI correlation data, but plotted differently. And this also shows a few things. Here we're looking at two different vial stopper combinations. Again, looking at the residual seal force, different sample sets. So actually what we're plotting here our residual seal force sample set. So starting from low residual seal force, these are loosely capped and crimped vials, up to the high capped and crimped vials. So you can see 4 different capping settings were used here to produce 4 different RSF groups, going from low capped or loosely capped to tightly capped. And the red data points are samples that lost CCI after deep cold storage or during deep cold storage. And so you see that for the first vial stopper combination, if it's loosely or even nominally capped and crimped, you get a high number of failures. Once you reach tightly capped and crimped, those samples are holding good CCI. For vial stopper combination Y, you actually see good CCI over the full range of RSF values. So clearly a more robust vial stopper combination when it comes to deep cold storage, also as a function of the vial sealing. And again, the key here is to have robust statistical data giving full insight into sealing performance of the production line. So you get insight into your process, but you also want to get that correlation to CCI performance of the primary packaging components in the deep cold storage. Finally, one last RSF CCI correlation graph, and this has, again, a slightly different story. This data was generated on real GMP product. You can see a reference there from, this was presented last year at a packaging conference in Venice. And the story here, you had 4 different batches of GMP product, and the capping and crimping process was actually changed between the first 3 batches and the final batch, batch 4. And indeed, you see in the RSF values that are plotted here, batch 4 samples having, on average, higher RSF values, meaning that they were more tightly sealed by the production process. The first 3 batches had lower RSF values and correspondingly more CCI issues. So for low RSF, you see that leaking vials tend to have low RSF values. You see that in this graph. And in fact, this data triggered an inspection process of these GMP batches. And if you look at the results of the CCI testing of these GMP batches, so here's the result testing batches 1, 2, and 3. A CCIT test method, again, was developed and validated for based on a CO2 detection. You see issues, CCI issues in the first 3 batches, but not in the last batch. And so the point that I wanted to make here is that it is possible to develop a CCI method for GMP product. And in fact, the requirement here was that the product would not have a temperature excursion of more than 60 seconds. So the CCI test had to be done within that 60 seconds, but it was possible to do that and generate the data, giving insight into the quality of the batches. I wanted to draw a link to the evolving regulations. The previous slide was actually an inspection process in the GMP environment. We've mentioned USP 1207, and just pulling out a key point from that chapter. When possible, use deterministic analytical test methods to build up a database on CCI throughout the product lifecycle. Hopefully, these concrete examples have shown you how you can do that with deep cold storage product. And this is generally applicable, by the way. This you should be doing with every product. If you look at the draft text for the EU revised Annex 1, I've highlighted in red some parts of the paragraph having to do with the CCI testing requirements in the annex. The frequency of testing should be based on the knowledge and experience of the container and closure systems. A scientifically valid sampling plan should be utilized. Sample size should be based on, among other things, process knowledge. And reading between the lines here, you can see that the regulator is actually making an implicit requirement on development to generate data so that you build up knowledge about the container and closure system, and you build up knowledge about the process. So again, I hope these concrete examples give you ideas of how you can build up this knowledge about your container closure systems and about your process to meet these evolving regulations. And finally, FDA guidance on process validation. It talks about generating process data leading to statistical confidence in the process. So how do you do that? How do you generate this data? Make sure it's robust so that you have statistical confidence about what's going on. I'll end with a slide on some future deep cold storage CCI topics, looking a little bit to the future. You actually currently see this now. There is a rise in the use of polymer vials for deep cold storage applications. Studies have shown that they can deliver good CCI performance. I think partly based on the fact that a polymer vial will have a similar coefficient of thermal expansion as the rubber stopper, so you might have a less risk for these interference gaps. There's also been some very recent work done showing that at the polymer to polymer interface, you could get some extra sealing enhancements going on. So, you know, as far as CCI is concerned, polymer vials are being increasingly used. You'll need to make sure that they also meet your other requirements for your formulation. Talking about new container designs, there is current work going on looking at new design features of the vial neck and also of the stopper that could perhaps help enhance CCI performance at the deep cold storage temperatures. I think we also need to look at completely innovative containers for this application, but the challenge here is to match existing filling lines, because a lot of people will want to, of course, continue to fill and leverage their existing filling capabilities for this product. But certainly a lot of work can be done there. And finally, there's also current interest in CCI of syringes in deep cold storage. Obviously, once you fill things in vials, you want to look at how you want to do that in syringes. But this is a more complex system than a vial. You know, where's the risk for a leak? You've got both the tip end and the plunger end. You have all kinds of configurations. If you look at actual product syringes, if you look at the expansion of frozen product and going down in temperature, you get an underpressure of a gas headspace potentially, and these two things may cause the plunger to move during deep cold storage. So more things to do here, and so certainly a lot of work needs to be done in this area in the upcoming period. Okay, wrapping up with the main conclusions. I hope that we've been able to raise awareness and show that, you know, the closure of these vial closure systems, they are affected by deep cold storage temperatures, so you need to generate the data to make good choices. I hope we've shown you that, you know, analytical CCI test methods can be developed that enable the generation of robust deep cold storage CCI data throughout the product lifecycle, also on real product in the GMP environment. And finally, I hope that we've been able to show you or give you ideas for a holistic approach to minimize the risk to CCI of deep cold storage product. And this involves generating science-based data in two main areas, or science-based data that enables you to do two main things. And number one, select the appropriate primary packaging components. And number two, really robustly qualify the vial sealing process. Okay, so those hopefully summarize the presentation for you. If you want more detailed information on this topic, we are publishing an ebook on this topic, which will be available soon, hopefully in the next week or so. If this is of interest for you, to you, you can request one at the following link that's on this slide. So take a photo of the link. I think perhaps we're going to try and share the link also in the chat session. But go to that link and request the ebook. You can also submit additional questions to CCIT experts at lighthouseinstruments.com. I mean, I see that we're running out of time here. We didn't leave as much time that we would have liked for Q&A. So if we don't answer your question in the Q&A session here, please send them to that email address. Okay, we can perhaps take a few questions here, and I'm going to pick out a few to answer. Again, if we don't get to your question, please send it to us, and we'll correspond back over email. So here's one question. Hi, Derek. So in essence, the primary risk of deep cold storage for CCI is a vial overpressure as opposed to a microbial contamination. So that's a very interesting question. I'm not a microbiologist, but I think it's probably safe to say that there are not a lot of microbes in your -80 freezer. Again, consult your internal expert microbiologist on that. So yes, a risk is this overpressure, and at administration that can cause problems, of course. I would say that if you're shipping on dry ice, another risk is to your formulation coming in contact with CO2. CO2 can perhaps change the pH level there. So, you know, you've got that interaction risk if you're storing on dry ice, and then the overpressure risk, probably not so much a microbial risk. Another question along those same lines, is there a link between gas ingress and microbial ingress? Yes, there is. That's, I think there are a lot of studies that have tried to show this, and you can show this to a certain extent, but it's very difficult. And I think the industry has always talked about size of leaks, because if you have a leak that's larger than a microbe, there could be a microbial contamination. But there are also lots of other parameters that affect if a microbe will ingress into your container or not. You know, is there a liquid pathway that will allow the microbe to move, et cetera, et cetera. That's a little bit more of a difficult question to ask or to answer objectively. I think we can point you, though, to some references of some studies that have looked at this. And finally, let me take a final question here. I see that we're over time, so let's do one final question. Hi, Derek. Does the stopper reseal so quick at room temperature that the ingress gas has no chance to escape? Another good question. We have measured overpressures that go up to about 1.5 atmospheres. And again, from the ideal gas law, you can theoretically calculate that the overpressure that can theoretically be achieved is 1.5 atmospheres. So in that particular case, in that sample, it looks like it resealed really quickly and trapped all of that cold gas inside. I think it depends on what kind of defect it is and how quickly the stopper will reseal itself. But in general, it does happen pretty quickly, and you will always actually reseal some of that storage environmental gas inside your container. I think it would be an interesting science project to really try and see in time when a vial reseals, but that's a complicated science project. So good question there. All right. Again, thank you everybody for joining. We are over time now. Again, if you have additional questions for myself, for Roger on RSF testing, please use the email address there, and we'll get back to you with some answers. Thanks again, and hope this webinar was useful, and hope to hear from you soon. Thank you.
Thank you. Have a great day, everyone.